design. And today we will be speaking mainly about the structure-based drug design. And we start with the molecular docking lecture run by Federica Moraca from University of Neapoli, Federico II. And I leave it to you.
Thank you. Thank you so much for the introduction. So, good morning, everyone. First of all, before going inside into the lecture, I would like to thank all the organizers of this event. This is my second year at this event, and I really enjoy it, the city and also the event. So I really appreciated the local organizer for having invited me for the second year. So basically, before going inside, I would like to introduce who I am, and where I came from. I came from the University Federico II in Naples, especially from the Department of Pharmacy. And this is the research group where I work, and we are the biomolecular simulation and drug design group. So we are basically involved in several projects founded by European Union and also by the Italian Minister of University and Research. And we are we are doing a lot of research concerning the food project, which is related to the increase of the quality of the food. So it's related mainly in food chemistry and also the RNA gene therapy. And so we are involved also in the design of small non-coding RNA for the improvement of gene therapy and how we can deliver this kind of drugs. And in our projects, we are mainly involved in molecular docking, drug design, but also structural biology projects. In particular, we are performing, in our lab, we perform both biased molecular dynamic simulations and also biased molecular dynamics. And the aim of our projects are related not only to design some and improve the optimization of ligands, but also to understand the implications for their biological functions. For instance, here we can see how the movement of the ligand, dynamic of the ligand, can change the geometry of this short alpha helix to induce inactivation of the receptor. Here we have studied the binding of this approved drug, is netarsudil, to the RNA-G quadruplex involved in the SARS-CoV-2, which is in the SARS-CoV-2 virus. And finally, we are also running some biased molecular dynamic simulations in order to improve the binding and unbinding process of a ligand. In this case, we have a ligand binding in a molecular target involved in the pancreatic adenocarcinoma. So we are, at this moment, we are running funnel molecular metadynamic simulations, and in order to study this kind of a binding and binding process, and so on. I just introduced this kind of project because the common key of these projects is the recognition of the ligand within its target. And this is very important because molecular docking is probably the most important starting point for a drug design process. On Monday, we have seen the lectures of Professor Kirkmar, in which we have seen that it is possible to design molecules and improve the optimization of the molecules, even we do not have the target, so even when the target is unknown. But we can also do the same when when we know the target, and especially when we have the availability of PDB structure or NMR X-ray structure or NMR structure. So the process known to define the binding of the ligand within its target is known as molecular docking. And this kind of recognition have a lot of potential use, so in the drug discovery, drug optimizations, but also peptide optimizations, and also nutraceutical research, because we can apply also molecular docking in the discovery of new functional foods. And so it is, I think, a quite reliable method that can have a lot of potential use. So basically, which kind of docking do we have? There are several types of docking. And basically, we can divide them in the blind or global docking, in which we do not know. We have the target, but we do not know where the binding site is. So in this case, it is very useful to, the trick in this case is to create our grid box large enough in order to accommodate the entire protein or DNA surface, and to have several spots in order to hijack the ligand into the several binding sites. So one of the main problems of this kind of approach is that in order to reach the most favorable protein-ligand complex, the energetically favorite one, we have to run several trials or several docking procedures. So it could require a lot of time. But we have also the FOXed or local docking, in which we know the binding site, the specific binding site from experimental structure, for instance, and so we need one spot to hijack the ligand directly into the spot and analyze which are the main interaction between the ligand and the target. So in this case, we have to pay attention on the quality of the binding site, because the docking accuracy is based on the input information of the binding site. So high is the quality of the model. High we have information of the ligand complex interaction. So, and it's also very important to set up the grid box in order to try to center the grid in the center of the binding sites. So other types of docking are mainly divided into rigid docking, which is based on the lock and key concept introduced by Emil Fischer, and in which basically he said that the recognition of a ligand against its target occurs especially when the ligand has a very good complementary shape with respect to the shape of the binding site. So only the ligand with a favorite complementary geometry can bind the target binding site. On the contrary, we have also the induced fit docking or flexible docking, in which we can treat the ligand as flexible, but also the receptor is flexible. And in particular, we can add some flexibility in the residues within the region of the binding site. So we can have not only the flexibility of the ligand, but when the ligand recognizes the binding site, also the receptor can accommodate the shape of the ligand within its binding site. So when we do have to start a molecular docking approach, which are the main steps on which we should follow? Basically, we can divide the three main steps. The starting structure, so we have to pay attention on the quality of the model. When we do not have the PDB structures, but we have a very high sequence homology, we can create the so-called homology model, and then we have to pay attention on the ligand. So let's see the first point and say a word about the quality of the PDB structure. So probably this is the most important step of a docking procedure, because especially when we have to deal with X-ray structures, we have to analyze, as I said before, the quality of the PDB structure. So in the PDB, there are a lot of macromolecular structures, but especially for the X-ray, most of them are not of high resolution. So it is very important to choose the model with a high resolution, because when we have a low resolution, we cannot have a real clear definition of the residues. So we have only the electron density map around the shape of the model of the residue, but we cannot understand which residue it is, so there are a lot of inaccuracies. But when we have very high resolution, like PDB structure of 2 angstrom or 1 angstrom, in this case we can have a very high definition of each residue. So it is important, when possible, to choose molecules or PDBs with a very high resolution. Another question to solve, so look at the electron density map. Another question to solve, to deal with, is how to treat the protons. So when we download the PDB structures, when we have X-ray, obviously, always we do not have protons inside. So we must add the protons, and we must predict them as good as possible. So it could seem like, you know, a simple question, but it's not really a simple question, because we cannot consider also the protonation state, probably at physiological pH, but we can add, we can consider also the tautomers. So it is very useful to consider all the tautomer states of some residues, because sometimes protons plays a very critical role in the recognition of ligand within its target. So let's go to the second step. When we do not have a good crystal structure, so we have to consider an homology model. And so if we have a query sequence, we can you know, create an homology sequence, and then build our structure that is obviously need to be validated. And it is important to see that when we have this kind of problem, we have to consider the percentage of sequence similarity, because sometimes when we have a very high percentage of of sequence similarity, we can apply some of these web tool, like for proteins or for DNA or RNA to build or predict the 3D structures. But when we do not have a very high sequence identity, we cannot apply classical approach for homology models. So it is better to consider the more advanced methods, and so we can use the newly developed AlphaFold that has a lot of agreement with the predicted one and the experimental one. So if we don't have a very high percentage of similarity, so let's use AlphaFold. And my suggestion is, in this case, to run a short molecular dynamic simulation in order to see and to achieve an ensemble of PDB structure to be docked. So let's use AlphaFold. So last but not least, how do we treat the ligand? Obviously, when we have a co-crystallized ligand inside, it is much better inside a PDB. It is much simple to optimize a ligand, but it is not always the same the case. So we have to get in most of the situations we have to get the ligand into the pocket. And when we have to do this process, obviously we have to consider how many conformers or how many torsions or rotatable states does the ligand reach in the unbound states. So the first approach is, the first question or the first problem to deal with is, okay, let's see how many translation and rotational movement are performed by the ligand in the translational and rotational space, and how we can optimize them. So how can we reach the optimal geometry of the most energetically stable geometry of the ligand, and the same also by considering the torsions. So how can we deal with how can we optimize the problem in the torsional space? So this is very important. This point is very important because from the ligand conformational sampling derives the right binding mode. And in this case, when we perform conformational sampling, we do not know the binding affinity of the ligand within its target. We only know the internal energy of the ligand. So it is just a method that tells us, okay, this conformation is good and this conformation is bad. And this tells the software to use this kind of conformer with respect to a better one. So it is important because from the ligand conformational sampling derives the right placement of the ligand within a binding site. So let's consider the ligand torsion profile before performing docking calculation. And then there are two pillars of docking, so the search algorithm that find the most favorable conformation of the ligand, and the scoring functions. The scoring functions are related to the docking software, and okay, they calculate the binding affinity within between the ligand and the target. And it is very important in this second case to, before performing a docking calculation, to do the so-called redocking, so to just evaluate the performance of our software and to see the capability of the software to reproduce the experimental pose with respect to the docked one. So it is very important to make this kind of calculations before docking. So how many research algorithms, ligand search algorithm do we have? Basically, we can divide them into systematic or stochastic. In the systematic search, the torsions and the rotatable bonds of the ligand are mainly by gradually changing the degrees of freedom of the ligand, while in the stochastic, the conformational sampling is performed randomly, and in this case, the two most important algorithms are the Monte Carlo search and also the genetic algorithm. With that, this last one we will see then later, and it is the searching algorithm of Autodoc. So, this is the software that we will use in the tomorrow in the afternoon session. So, what about instead the scoring functions? Scoring functions are instead divided into 4 groups, and they are very different between each other. There are, for instance, force field-based scoring functions in which the energetic contributions of both non-bonded interaction and bonded interaction are evaluated by considering the van der Waals force, hydrogen bonding, electrostatic bonding, and so on. And they are based on a specific force field. For instance, in the case of Autodoc, they were calculated from the amber force field. In the empirical function, we have just the energetic contribution are obtained by just sampling the weighted contributions between the energy evaluations, and knowledge-based, which is the main scoring function of Autodoc Vina, are derived by the structural collection of the structure information between already existed protein and ligand complexes. And finally, we have the consensus, okay, that we will see better later on. And okay. Which kind of, the question now is, which kind of scoring function do have to use? It depends if we have to consider the speed or the accuracy, because speed and accuracy of the docking are also two very different situations. So there are some scoring functions that are very fast, like the empirical scoring functions, but there are some scoring functions like the force field based and the consensus that are quite slow, because we will see later on, because they consider the desolvation term of the energetic contributions, so they are slower with respect to the others. So we have to deal basically with these two kinds of situations, if we want speed or accuracy in our calculations. So here we have again the scoring function, the description of the scoring function. So let's see the case of Autodoc, which is force field based. As I said before, the affinities between the ligand and the target is estimated by considering the strength of the intermolecular interaction, specifically for the van der Waals term and the Coulombic term, and also by considering the hydrogen bonding term and also the desolvation term. And the main advantage of this kind of scoring function is that it is physically based. So, as I said before, it derives from Amber, but the main disadvantage is that sometimes electrostatic terms are often overestimated. Then we have the empirical scoring functions that are inside the glide docking software, in which we have the sum of each internal energy contribution of the ligand, and it is also the term inside these kind of scoring functions. And in order to introduce also the entropic loss in the contribution of the binding, then we have the knowledge-based scoring functions like AutoDoc-VINA, and they are mainly based on the creation of the grid box around a collected complex coming from the PDB structures, so from experimental co-crystallized ligands. So in this kind of scoring function, a grid box is built against the complex, experimental complex. So, and in the docking functions, basically we calculate the Boltzmann probability of find a specific probe atom in that specific 3D coordinates, especially, for instance, carbon atoms or nitrogens or oxygen atoms in that specific position. So this is very related, as I said before, by the Boltzmann contribution. So highest is the probability, and highest is the binding affinity calculated with its target. This is a very useful scoring functions, and that is implemented in the AutoDoc VINA function. So we have seen the main scoring functions that characterize each docking software or each algorithm. And okay, but which kind of scoring function do we use? So it's the same problem as the ligand. So have I reached, in the case of the ligand, I must say, okay, have I reached all the conformer? Have I explored all the torsional, all the conformational sampling of the ligand, and which algorithm is better than the other one? The same is done for the scoring functions. And this is a key element of the docking, because sometimes scoring functions does not treat the binding affinity. As we have seen, the scoring function does not treat the binding affinity in the same mode. So, and the problem is that, okay, in the ideal case, each scoring function or each docking protocol should be able to rank only through it at the beginning of its ranked list. So the perfect algorithm, in the perfect algorithm, we should have all the top ranked list of the ligand active, experimentally active, okay? So this is the perfect situations, but in the real application, this never occurs. So often the top ranked ligands are not experimentally active. This occurs in every time we do docking. So, and why this? Because ligand molecular recognition process is a really complex process. It could be simple to treat, but it is governed by a very different process. So we have to deal with the entropy or scintilla data and the absolute binding free energy. So there are a lot of things that hampers to reach this kind of situations. And sometimes all the scoring functions that we have seen before make approximations to evaluate the binding affinity. And so this is the point between the speed and the accuracy that I said before. But there is a way to deal with this problem. So how we can reach and how we can improve the scoring functions, how we can reach how we can do in order to have the top-ranked molecules to be experimentally active. One possible solution is a comparative study of the docking scoring functions. So this is why I said the problems of the accuracy of the docking. Because in this case, when we apply this kind of solutions or this kind of study, we always refer to the consensus docking. So the best thing is to compare the several scoring functions and to make a sort. This is a very nice paper of Palacio Rodriguez and co-workers in which they introduced, for instance, the exponential consensus ranking, and in which basically they say that the best thing to do the consensus docking is to perform, given some structures and some molecules, performing docking calculation with different softwares, with different scoring functions, and then merging all the hits in order to create, to make an exponential factors that will rank the molecules, the ranked molecules coming from each docking program, and then we will have the final score as the sum of the single exponential score of each program, and so ranking the final consensus score. And this could reduce the number of false positives to be found during a docking procedure. So this is, I think, one important solution to deal with this kind of problem instead of selecting a lot of ranked molecules to perform experimental assays. So now we have now that we have seen some scoring functions or search algorithms, so what are the main features that the docking software to have is the sensitivity of the parameters. So is the sensitivity, with sensitivity we refers to the inclusions of the starting conformations of the ligand as starting point for calculating the the binding affinity to the target. Adaptability in order to add other scoring functions. Ability for refined docking parameters. The speed usually is better to have a user interface for a docking program, and the code availability. For this last feature, we will have here I summarized some of the most used docking software, for which most of them are free, like Vina and Autodoc. Most of them are commercial, but they are also treat the docking in very different way. So having probably the availability of the software is probably a very good starting point to make docking as simple as possible. Let's start now, and this is very useful for the afternoon session, to speak about some main features of Autodoc and Autodoc Vina in order to perform the tutorial this afternoon. So I will briefly introduce some characteristic of this kind of software. Basically, the Autodoc suite is characterized by two parts. The docking engines, which are mainly we will use mainly Autodoc and Autodoc Vina, but also we have also the Autodoc FR for the flexible receptors to perform in-the-suite docking, and Autodoc Crankware PEP to perform docking using peptide. And also it is characterized by tools. We have a graphical user interface. Here in the tutorial we will use the Autodoc's tools and the docking methods. So there is a part of the Autodoc to perform the covalent docking, and also there is a tool inside the software to predict the binding site, which is AutoLigand, but here in the tutorial we will use AutoGrid, which creates a grid box. Once we have defined the ligand binding site, we have it is an algorithm that performs the calculation of a grid box around the ligand binding sites. So there is a new implementation of Autodoc, which is Autodoc GPUs, which is very faster with respect to the single CPU docking. So there are no difference in the scoring functions or in the search algorithm, but the only thing is that you can run Autodoc in GPUs, so you can speed up your calculations. And okay, let's see how Autodoc treats the receptor. As I said before, it uses AutoGrid, so it creates a grid map within the binding sites, and it creates the grid box is created by considering each atom type of the ligand. And it calculates also the electrostatic potential and the dissolution energy in order to improve this kind of calculations and put these two contributions in the finally binding affinity score. And in this step, the general rule is to create the grid box, the grid volume, large enough to allow the ligand to rotate freely, because Autodoc performs a genetic algorithm searching conformational sampling, so we have to consider all the conformers generated, and so it is better to use a grid box large enough. So how does Autodoc treat the ligand? Basically, Autodoc is characterized by two conformational search methods, which is the local search and the global search, known as the genetic algorithm. But it is also characterized by a third conformational search method, which is hybrid and derived from the combination of these two search algorithm, which is the Lamarckian genetic algorithm, which is the most an improvement of the genetic algorithm, because if we see here the potential surface, we can see that in the genetic algorithm, from the starting conformation of the ligand, we generate, you know, the child conformer, and only that one are used to perform the the docking calculations, but in the Lamarckian genetic algorithm, for each conformer that we have generated, this algorithm generates a lot of next generations conformer, and each of the next generations we perform a local search, and for each conformer we can, for each child, we will perform the docking calculations. So the ligand conformational sampling is really improved. And my suggestion is to see about the rotatable bonds of the ligand. So more rotatable bonds in the ligand, more difficult will be to find a good binding mode. So increase the number of the evaluation of the conformers, so the next generation conformer, in order, especially when we have a lot of torsions, in order to explore as good as possible all the ligand binding modes. Once again, another thing that we have to consider is the partial charge. Basically, Autodoc calculates the ligand partial charge in two ways. We have the Gastiger calculation and also the Coleman. In the Gastiger mode, ligand partial charges are calculated on the considering the molecules' electrostatic potentials and summing over the atomic electron density in the molecules. On the contrary, the Coleman method is based on the Amber force field, and it calculates the ligand partial charges considering the molecular orbital electron density. So it is, the second one is more physically accurate. This does not mean that we have used more Coleman with respect to Gastiger. So the suggestion is that the choice of the method that we have to select depends on our specific requirements. So also in the complexity of the ligand, and in if we have to consider if we have enough time to perform Coleman charts. It is sometimes also useful to perform both this kind of calculation and also to see the difference, or if there is a convergence of the results. So here, let's translate what we have seen before in the main Autodoc file, which is the docking parameter file, which is basically made in this way. So we have this section, which is related to all the grid map, considering specific atom type of the ligand, but also we have the electrostatic contribution map and the desolvation contribute. So then we have information about the ligand in the PDB-QT file, the center of the ligand. Then here we have the information about the coordinates of the ligand and the Hermes deviation tolerance if we have to perform the cluster analysis. So by changing this value, we will have a different clusterization of each binding mode. So in this part, we have all this section is dedicated to the genetic algorithm, so to the modulation of these kind of parameters will introduce an exact number of the conformations. So depending on how many torsions or rotatable bonds has the ligand, we should deal with this kind of parameter in order to increase the number of the next of the child, so of the next generation conformer, and the evaluation of the of its generation. And so we have to modulate all these kind of parameters to deal with the genetic algorithm. Then in this part instead we have the local search, and so parameters for the local search. And finally, by combining this section with this one, we will obtain this string that tells to Autodoc to perform the search conformational search with the Lamarckian genetic algorithm engine. So how does instead Autodoc work on the complex? As I said before in the beginning of the lectures, Autodoc is a physical-based program, so it is based on the Amber force field. So as I said before, it is characterized by scoring functions with van der Waals, electrostatic, directional hydrogen bonds, potential, and all these kind of factors are derived from the Amber force field. What about instead Autodoc-Vina? Which are the difference between Autodoc and Autodoc-Vina? Autodoc-Vina can be considered as an improved version of Autodoc because it is characterized by a different search algorithm and also a different scoring function that assure both to reach an accuracy level, especially when we have ligand with a lot of rotatable bonds. We have very low Hermes D value, and also it deals with the speed. So since it is based on the knowledge-based scoring function, Autodoc-Vina is faster than Autodoc. So it is the best compromise between accuracy and speed. Here we have some difference between these two kind of algorithm, between Autodoc and Autodoc-Vina. We can see that in Autodoc-Vina we have a different scoring function, search algorithm, and different scoring functions, and also the treatment of the receptor is different, because while in Autodoc we have to calculate separately the grid map, in Autodoc-Vina this is performed internally. So we do not have to create some map, but it does calculate automatically. However, in the new version of Autodoc-Vina, the new version of Autodoc-Vina, these two kind of software are closer between each other, and because we have in this new version we have the unification of the features of Autodoc in Autodoc-Vina, and in particular we have the possibility to add in Autodoc-Vina new atom types. We have the possibility to load external grid map files, so we can load inside Autodoc-Vina the grid map calculated with Autodoc. There is the possibility also to include explicit water molecules, maybe calculated also with a hydrated algorithm of Autodoc, and also the possibility to sampling macrocycles. So this is a newly improved version of Autodoc-Vina. So before starting the tutorial this afternoon, we will see just here how a little workflow of how performing the docking study. So we have the starting PDB structures and the ligand. So we have to perform conformational search. Then use one of the two or both of them docking software to compare, to have a consensus scoring, performing analysis of the docking outcomes, and both be considering the binding modes and the score, and just to select the best binding mode finally, and analyze what does it happen. So, in conclusions, I would say that the determination of the binding mode between a ligand and a target is crucial, is probably the most important step in the drug discovery process. We have a lot of docking algorithm, a lot of docking software to deal with this problem, with the docking, but each of them is characterized by different scoring functions. And the scoring function is probably the most important part of the docking procedure. And no perfect docking scoring function exists, so it is better to understand that all the current scoring functions that we have some advantages and limitations, as we have seen. So let's try to perform the consensus scoring as a possible solution to overcome this kind of limitations. And with this aim, it is very important to use, I suggest you to use one or more docking software to predict the binding pose and then to perform the consensus scoring. And so now I would like to thank of you for your kind attention, and now it's time to dock. So let's see this afternoon for the tutorial, and obviously if we have any questions, I'm available. So. Other questions? Yeah.
So when we don't have a structure and we do homology modeling, nowadays, does homology modeling still win over the AlphaFold?
Yes, yes, absolutely. Yes, AlphaFold, as I also said, is a very useful instrument to deal with homology model problems, especially when we do not have a high similarity, high sequence similarity. Yes.
The new version also has peptide docking. How long peptides it can dock?
Do you mean the new version of Vina?
Yeah.
Yes.
How long peptide can it dock?
I'm not actually sure about the length of the peptides. In my experience, I have docked at least peptides with 12 or 15 amino acids, and it worked. So I think that it will depend of how many rotatable bonds there are in the peptides. So I think that maybe longer is the peptide or the protein, and longer is the time required. So, but I deal with this calculation.
Can it handle cyclic peptides?
I think so. Yes, I think so. Yes.
So anytime I want to do docking, I always have like a database full of smile codes, smiles.
Yeah.
And probably you need to convert it from the 2D smiles
Yes.
to 3D structures.
Yes.
Is this implemented also in Autodoc? Some kind of a ligand preparation tool?
Not yet. You cannot use SMILE file to convert in PDBQT, but you have first of all to convert the SMILE or in a MOL2 file and then in PDBQT, or in a SMILE file to PDB and then PDBQT.
What do you use for the conversion?
No, the type of file. When you start from the SMILE, you can use some kind of software, like, for instance, OpenBubble, that is also free, so you can download. And you can convert the SMILE file to the MOL2 extension or to the PDB, and then use the command line of Autodoc to convert MOL2 or PDB into PDB-Qt. There is no possibility to convert directly the SMILE in PDB-Qt.
Okay. So how do you? There's a problem with protonation states, tautomers, and stuff. Like if you get it converted to 3D, how will you actually like prepare the ligands to be?
Okay. Yes. You have to. Yes, you have to do this kind of conversion, this kind of modifications just before you to convert in PDB-Qt. And there are some software that can do this, like the Chemaxon software, like ChemDraw, can evaluate the protonation state of the ligand at and different pH. So yes, you will have a lot of protonation states, but also there is some Schrödinger tools like LigPrep or EPIC that can automatically calculate the protonation state. Yes, but you have to do this before to convert in PDB-Qt.
The main problem with LigPrep, because I work with Schrödinger, is that you cannot really feed it with 2D structures more than, I don't know how,
Yes.
thousands of structures, otherwise it will crash.
Yes, there is with LigPrep. I encountered also this kind of problem. So it is very useful when you have a lot of ligands. So when you, for instance, when you have to perform virtual screening, so you have to perform a lot of molecules, the docking of a lot of molecules. So LigPrep is very useful. However, I think that when you have to deal with with a small set of molecules, it's better to see, to see better the protonation state, maybe using, different or to compare different software in order to see if LigPrep or EPIC are predicting well with respect to other one. Yes. Yes.
So if you, let's say, really want to use an AlphaFold model, what can you do to maximize your success with it? Maybe do some MD simulation prior? Or
Yes, I would just, I suggest to use AlphaFold, obviously, when you don't have the structures. But my suggestion is to perform short MD simulations, not so long, in order to consider it also an ensemble of docking structures. So, because in AlphaFold we do not know if that atom is in that position as, for instance, in X-ray model. So it is better to have an ensemble, in my opinion, obviously, it's better to have an ensemble of docking structures. So perform few nanoseconds of MD simulations, yes.
is it possible to maybe also combine it with homology modeling and use maybe homology modeling
With AlphaFold?
side
With
and
AlphaFold? Yes, I think so, yes. Yes, I think so. It is...
you haven't tried it?
Not yet, because when I do sometimes an homology model, I look the quality, the parameters of the quality of the model, homology model. So then I used it, but it is possible if there is also the AlphaFold structure is very useful. um, in this time, so in these few months, I'm actually using AlphaFold also to predict how mutations in a target does change the conformation of the target. So I think that it is very useful also for this kind of problems. So I really trust AlphaFold. Yes. Other questions?
Yeah, maybe if I can ask, while we are already talking about AlphaFold. So AlphaFold 3 claims to be really good at predicting protein-ligand complexes. So as a molecular docker, what's your assessment of these really great metrics that they show, where they have 80% RMSD under 2 and so on? What do you think about this?
When there is a ligand inside?
Yeah.
Yeah, my suggestion is as I said before, when there is not a ligand inside in AlphaFold, so it is better to compare if you have also the PDB structures. It's better to compare, or maybe to always doing MD simulations, so to deal with and to try with the ligand to which conformer of the structure is best to bind the ligand. So in this case, short MD simulation could be useful.
Yeah, thank you.
Yes.
It's not a question, it's a comment to the previous question actually. With AlphaFold 3 you can do this, but it would be so slow that you can only afford like 10 compounds. And this is a difference. That's what I was talking about yesterday. So it's like 20 minutes per complex, depending on the hardware, of course.
Okay.
So talking is like two orders of magnitude faster.
Okay. I didn't know. Okay, if there are no other questions, I can leave the session to the next one. Okay.
Do you hear me? Does it work? Okay, it seems to work. Anybody knows how to open it full screen here?
I think it's something like maybe Control N or Control Shift N, something like this. It depends on which PDF.
F11 doesn't work. This was the first what I tried.
On the top left menu, maybe. If you go to menu,
Okay.
the very left side,
Okay.
view somewhere,
Zobrazit.
Which?
In the middle.
Zobrazit, yeah.
Okay.
And then
And then?
This one. Up.
Yeah.
Okay. Control. Well, right.
okay, close.
I'm Linux guy, sorry.
Okay, so I will speak about molecular dynamics. This would be a really very simple introduction. So if you're already familiar with the technique, and if you ever try this, you will probably be bored to listen to this. So please feel free to go and do something more useful for you. So we will start with a plan. So in the beginning, as usually, I like to provide a little bit of philosophy in general apply about this technique, why it is needed. Then we will speak about classical MD, a little bit of theory, almost without the formulas. And then I will speak about which phenomena could be simulated, and will provide some examples of applications in the drug discovery. So first, when we're speaking about MD, the first question, is this experimental technique or theoretical technique? And if we will speak about this, so the experiment is our ground truth. It's quite expensive, it's quite complex, but it provides you actually the vision of the nature, the best one we can get. The theory is simple, it's cheap, it's most fundamental, but again, it's too general, it's complex math most of the time, and it's hard to apply. And simulations are somewhere in the middle. So you are applying the theory to concrete systems by simulating them using computer power. And usually these systems are too large and too complex for the analytical theory. So if we will rephrase what Stephen Wolfram said, that simulations is where the theory becomes very complicated to the extent that you cannot predict what you get, and you need to approach it like an experiment instead. So basically, it's based on experiment, and it historically was considered as such, but now it's considered as a kind of third kind of things. So we have in vitro, in vivo, and in silico experiments. So most of the people approach this experimental technique, and really the workflow is experimental. So you prepare the system, you set up all the initial conditions and external parameters, you account for whatever you can account, and after that you let it run, and you don't know what you will get at the end. So only after analysis of the results you get some understanding if you did it correctly. So this is a kind of black box for you, and it's like a football match. You know all the rules, but you have no idea who will win and which results you will get. So saying this, there is a whole hierarchy of simulations, and MD is actually sitting somewhere in the middle. So you can start with a very precise quantum stuff, where you can operate with dozens of atoms on the time scales of picoseconds. Then you have all the spectrums of different quantum techniques to semi-empirical, ML potentials, whatever. And you are coming to the classical MD simulations. We are sitting in about the nanoseconds time scale, and the number of atoms from 100,000s to millions. And after that, you have coarse-grained MD, where you combine several atoms together, and you can go to much larger systems, up to milliseconds, and several millions, up to tens of millions of atoms. This is a mesoscale, and after that, you are going to continuum. And this continuum, you can simulate whatever you want, up to the size of the universe, if you are speaking about the classical fluid dynamics or electrodynamics. So we are in the middle, and we are in what is called the nanoscopic scale. So it's nano in the sense nanometers, nanoseconds to microseconds. So basically, what is classical MD and why it is classical? It's classical because we have no electrons, so we are working in the approximation of Newtonian rules of motion, and we integrate in the second Newton law, actually. And the system is modeled on the atomistic level. Here it should be an asterisk because this is not always true, but in the first approximation it is. And each atom moves according to the Newton mechanics due to the forces from all other atoms in the system, and it's pretty much nothing more. You only have interatomic interactions which are influencing the motion of atoms. Then you have to integrate this equation of motions numerically using the software, which is an MD engine. And you get the trajectory of each atom, which is a kind of motion in time and space. And this is recorded, and then it has to be analyzed and visualized. You get all these kind of fancy movies, and you need to make sense out of this mass of atoms which you get at the end. And what is important is that atom is a material point where you assign some mass and some charge. But there are no electrons, there are no orbitals, and no quantum effects, and as you can see, no problems, but it's not really true, because you have some problems. And the life without electrons can sometimes be hard, because first of all, you cannot simulate any kind of chemical reactions. Again, an asterisk here, there is a kind of force fields like ReactFF, which is designed to simulate chemical reactions, but this is kind of niche scene, so we will not speak about this today. So you cannot form the covalent bond, you cannot break the covalent bonds. But with ionic and hydrogen bonds, it's okay. Then you have no electronic excitations. So for example, if you're working with photochemistry, fluorescence, photosynthesis, whatever, you are kind of limited because you cannot model the excited states of the molecule and electron transfer phenomena. So no charge transfer as well. So all the charges are fixed. If your interaction involves some extreme polarization effects, you are in the trouble. There are ways to work around this, but in general, it should be avoided. And there are no funny quantum phenomena like umbrella undulation of the ammonium when you have the planar system and on average, but instantaneously it's either this or this, so you cannot do this. You are just working with the average geometry. But all the rest except these cases could be simulated. So again, how long and how large? Again, kind of scale, this time for the MD itself. And here you can see the evolution of this technique from 1990s. And the technique itself was originating to 1980s. And most of the software is from this era. And up to now, you can see that we actually spanned like 5 orders of magnitude in terms of the number of atoms. But again, what is shown here, kind of protocell, this is coarse-grained simulation. This is not atomistic by any means. So we operate with a large clumps of atoms treated as a single particle, but nevertheless, it becomes possible now. Important distinction here is what you can do as an average guy in an average institution, and what somebody can do having an access to the largest supercomputer in the world and the huge NIH grant. And this difference is like 3 orders of magnitude. So as an average guy, you can work on the level of millions of atoms and up to microseconds. The state-of-the-art setups can afford like 2 orders of magnitude above this. But this doesn't mean that you can rely on this. Nobody will give you money to do this in the real world. What is important with MD? We all understand up to now that it's very well complementary to biological experiments, because in experiments we rarely get the atomic resolution, and we cannot pick the atoms and actually observe the single atom or a single group of molecules. In MD you can do this. And you're also the God. So you're playing the God, you're controlling everything. You're controlling all the conditions. You don't necessarily know what will happen, but you can set initial configuration as you like. So it's 100% controllable. And it's very easy to play with the system even in the unphysical way. So you can change the atoms, you can mutate residues, you can change charges, you can invent whatever nature cannot do in your simulation. And you get quantitative results which are comparable with a number of experimental techniques like NMR, like X-ray, like cryo-EM. You can measure viscosity, diffusion, whatever statistical properties you want in your system and compare with whatever experimental technique is available to you. So now let's go to the theory. So as I promised, almost without formulas, so it would be a little bit superficial. So here is a general MD algorithm. So basically, you first set up your initial conditions, which consist of the interaction potential between the atoms, so all the forces, how one atom influences the other. Then you need the positions of all atoms in the system, and you have the initial velocities of all atoms in the system. The positions come typically from the PDB file or AlphaFold prediction, or can be composed by hand. Velocities could be generated. It's not really a problem. We know the Maxwell law, how for certain temperatures the velocities have to be distributed, so this is done internally. And the potential interaction function is the most interesting part. We will cover it a little bit later. And then you are doing the following. You are computing forces using the Newton equation of motion by summing up contributions of all other atoms in the system, how they influence one particular atom number I. This includes all the bonded and non-bonded forces. And after that, you update in the configuration of atoms by numerically integrating this equation of motion. And then you're continuing this many, many times, millions and tens of millions times to get the time scale of nanoseconds and microseconds. And periodically, you are outputting your velocities, positions, energies, temperatures, whatever you need. So this is a general algorithm. Of course, it's more complicated than this inside, as you can imagine. So for example, you have different integration techniques for this equation of motions. You have specific treatment of the long-range forces, such as electrostatic. You have specific methods for maintaining pressure and temperature. So let's go to the first one, which is how we treat the space, because this is not trivial again. Your system is limited by the simulation box, so you cannot work with an infinite volume as in the real life. And the only way to deal with this is to have the periodic boundary conditions. So you are actually duplicating your volume in all in the 3D space in all dimensions infinitely. And after that, you have what is called the minimal image convention, which means that for each particle, there is one and only one image in the other box, which is periodically replicated. This simplifies the things a bit and allows you to compute the forces quite efficiently, but still approximately. And the shape of this box could be either cubical or triclinic, and triclinic boxes are quite funny because you can get volumes like this, which are periodically replicated over the space, which is either rhombic dodecahedron or trichytid octahedron. And the reasons of doing this kind of funny shapes is to minimize the size of the simulation box. Because the volume of this figure comparing to the square box is about 30% smaller, having approximately the same distances between the images. So you can save like a third of your computing power. This doesn't work all the time, but for spherical particles like proteins in the solution, this is the way to go. Then again, for equation of motions, this a little bit in more detail. So you're setting initial conditions, you are computing the force, you are numerically integrating, but the size of your system is very large. So you have n atoms, like 1 million atoms, you have 3n degrees of freedom, and you need to solve 3n equation of motions, which means that the software which is doing this is among the most computationally intensive software out there. So before appearance of large language models, MD was probably on the same level as quantum techniques in terms of computational complexity and demands for computer power. Now we are on the third place, let's say, but we are still among the top usages of the computing clusters. So it's a very demanding technique. Then when you set up your system, when you have your box, your atoms inside, then you should consider that your system is small and your integration is approximate. So when you solve the Newton equation of motions, you have some error. So this is not exact, you always have these numerical errors, and that's why the velocities change a little bit, and the effective temperature of your system, which is determined by the velocities inside, actually drifts. So this system will either heat up or cool down, and you want to keep it at the constant temperature, like in experiments. And in order to do this, you are coupling your system to the thermal bus. There are multiple techniques how to do this, but actually the idea is that you have external heat bus, which is external to your system. You're not controlling it, but you are setting the desired temperature, and it acts like rescaling the velocities for you to keep the average velocity on the level which is determined by your temperature. Again, multiple techniques exist. Depending on the simulation software, there are different tricks, but this is a general idea. And the same things apply to pressure. Again, your system is small, and the volume of your simulation box determines how densely the particles are packed inside, so what is the pressure inside. And you have the correct pressure, again, you need to adjust the box size. So if the velocities increase, the box should expand a little bit. If velocities become small, it should shrink. And you do this by, again, coupling to external barostat. So it's pretty much like a piston with a weight which is attached to your system. and which keeps the volume of the simulation box to the desired level with certain fluctuations. There are a lot of theory on this, and there are a lot of quirks, like how much of fluctuations you want in terms of the pressure, and you can control this. But in a nutshell, is what you do, and the pressure coupling could be either isotropic from both sides simultaneously, or semi-isotropic if you have the membrane, or it could be anisotropic if you have some complex system. And now we are coming to the most interesting part, which is empirical potential functions, which describe interaction between the atoms in your system. And this is divided into two large classes, the bonded and non-bonded interactions. So for bonded interactions, you actually have the covalent bonds, the angles between the covalent bonds, and the dihedral angles or torsions, which are so important in docking. And you also have what is called improper dihedrals. And here you have the general, let's say, formula of the empirical potential for MD, where you have the bonded terms, the angle terms, and the dihedral terms. And in addition to this, you have non-bonded interactions, which are electrostatic Coulombic interactions between charges, and the van der Waals interactions, which originate from the quantum effects and which are usually approximated by the Lennard-Jones potential of 6 and 12th power of the distance between the particles. And as you can see here, there are quite a lot of parameters, like this case here, like this A and B parameter, like charges. All these parameters have to be taken from somewhere. And that's why this is empirical potential, because you are taking these parameters once, and you're running with them, and you use some empirics to get these values. Usually, oops, okay, so I see that okay, so no formulas, sorry guys, don't know why. So for bonds, you have one parameter, which is, okay, I will explain here. So for bonds, you have one parameter, which is force constant. For angles, it's typically, again, one parameter. For dihedral angles, there are many of them, because dihedral angles, as you can see, could be quite complex in shape. So you have several parameters for each of the harmonics. For non-bonds, you need to have charges. You also need to have electrostatic constants, the permittivity of your medium. And you also need the van der Waals parameters A and B for repulsive and attractive parts. And you have to take these parameters from somewhere. So I will need to skip this because it doesn't really work. Yeah, I will only stop here for improper dihedrals. So in addition to proper dihedrals, which look like this, which are rotations, rotable bonds, there are also improper dihedrals, which are planar groups, planar geometries. And you want to keep it planar for chemical reasons. So you have out-of-plane potential, which returns the system to planarity. This is a little bit misleadingly called improper dihedrals. And for van der Waals interactions, it becomes even more complicated because you have different particles. You have oxygens, carbons, nitrogens with different van der Waals radii. And after that, you need to combine them somehow together in the system because anything can potentially interact with anything. And for this, what is called the combination rules is used. So we will come to this a little bit later, but the potential itself looks like this. For electrostatics or Coulombic interactions, there is a distinction between short-range and long-range electrostatics. And the short-range or explicit electrostatics is only applied within the cutoff radius, typically about 1 nanometer. And all the particles which fall inside this radius from each of the particle which you choose as your particle which you are applying forces to are computed explicitly. But if you, for example, here this is a typical Coulombic potential, which is 1 over R, and you see that if you are going up to 0.9 nanometer and then you cut it off, you still have some residual potential, and the derivative here is not 0. And if you are doing numerical simulation, this could be a problem, so you have to put it to 0, and there are several techniques to do this, like reaction field correction or reaction field with shift. So in most of the MD packages, you have separate parameters to control this, but usually there is a kind of set scheme for this, for each of the force fields, and you are just using what people suggest. Another thing is a long-range electrostatic, which is taken into account approximately. It's an error here, it should be A. And it's also called the Ewald sum over periodic images. And the idea is that if you have your charge in the simulation box and you have replicated simulation boxes around, there is still electrostatic interaction between the images of atoms. And you have to take it into account somehow. So this is an approximate technique where you're summing the in the reciprocal space after the Fourier transform. I will not go into the details. So this is quite accurate, but still approximate. And this is called, in most of the times, you will use PME, particle mesh Ewald. In most of the packages it's implemented, and this is a way to go in most of the simulations. And it's applied only beyond the cutoff. Now, when you're working with MD, you are always speaking about force field. So what's a force field? Force field is a set of constants of the empirical potential that determined from either experiments or computed on the higher level, like quantum level, or it could be guessed in some way. So I mean, everything works if you get what you need. If you get the correct empirical values, it doesn't really matter where you get them from. Force field is, in a very broad sense, includes the functional forms of your bonded and non-bonded interactions. It contains the non-bonded combination rules, the rules for assigning angles and dihedros, because depending on the convention, you can enumerate all of them or only some of them. Also, it includes the predefined topologies of the standard molecules, like amino acids or nucleotides. The rules of parameterizing new compounds, which is very important if you get in the chemical entity which is not included into the force field, how you should parameterize it. What are the rules, which level of theory to compute the charges, what to do to get the van der Waals parameters, and so on. And also recommended MD parameters for running the simulations. And the common force fields are, for example, AMBER, CHARM, GROMACS, or PLS, and many more depending on your domain. So, in addition to this, there is also topology. Topology is a scheme of connectivity of your molecule, which you are simulating, and it lists explicitly the bonds, angles, torsions, improper dihedros, and also the atom types. And the atom type is kind of distinct chemical identity of the atom. For example, if you have the carbon, it's not just carbon, it's carbon in the six-member ring, which is aromatic, or it's nitrogen, which is non-aromatic, sp3, sp2, whatever. These are distinct chemical types. And it also defines the mass of the atom and the default charge, which you can override for your molecules, and the pair of non-bond parameters for van der Waals interactions. The atom types are kind of arbitrary, and they're assigned separately for each of the force fields. They are not compatible. The atom types for charged force fields are not compatible with AMBER types, so you cannot mix and match. You have to stick to one of the force fields. Typically, there are from 50 to 100 of them in the most of force fields. You can also define your own if it is needed. The way how to do this, again, differs among the force fields and simulation packages. And in some of programs like GROMACS, you can also override the atom type properties, but in CHARM or NMD, you can't. So it really becomes a zoo in terms of how you are doing this, independent of which program is used. And for example, this is how the topology looks like for a very simple molecule for water in the AMBER force field. So you have oxygen and two hydrogens. For oxygen, you have the atom type OW. You have the partial charge, you have the mass, and you have sigma epsilon, which is van der Waals parameters. The same you have for hydrogens. Both of them are identical, of course. And also you have the bond, which is a harmonic bond between oxygen and hydrogen, with this force constant and this equilibrium distance. This is in nanometers. And you also have an angle here, which is a harmonic angle. And again, it's an average 104 degrees, and this force constant. In other force field, it could be different. In other water model, it could be different, but it's how it looks most of the time. And this is how the topology for this water molecule looks in the package itself, in the topology file. This is GROMACS example. In other packages, it would be different. But it's pretty much similar. So you have the name of your molecule, you have the atom types here, you have charges, you have masses, you have atom types, which is distinct from the atom name, because atom name is what you have in your PDB, and the atom type is what you have internally in the simulation package to compute the interactions. Then you have the bonds. There are two bonds which are identical between atoms 1 and 2, 1 and 3, so oxygen with 200 hydrogens, lengths and the force constants, and some other parameters. And for the angles, again, you have the angle between 2, 1, 3, so hydrogen, oxygen, hydrogen, with the angle and force constants. A few words about MD packages. So there are several commonly used MD packages for different domains. So if you're working, let's say, mostly with solid-state physics and materials science, 99% of the times you will use either LAMMPS or DLP. Since we are biologists, we will use either GROMACS, NMD, OpenNM, Umbra, few other packages. And this is a distinction. So you can do the same with LAMMPS, but it's more tedious. So basically, you have to use a tool which applies to your domain. All modern MD packages are very well parallelized and also GPU accelerated. So typically, you want to use them on the computer clusters with GPUs because it will give you many orders of magnitude in terms of computational power. And the packages themselves are kind of marvels of software optimizations. This is one of the most optimized software on this planet. But usually it's terribly written. So it's bad in terms of software engineering. So if you don't need to go inside the source code of this, please never do this until you really need. I did it, and it's painful most of the time. A few words about the combination rules, which I mentioned previously. The rationale of this is that you have n atom types, and you have n squared parameters. So each particle type can interact with each particle type. So in practice, if you have 50 atom types, it's about 2050 combinations, and each combination have 2 parameters, so it is 5,000 parameters, which have to be determined empirically. It's not possible. You understand that it's not possible to get it from any kind of experiment. And in order to deal with these, a combination rule is introduced. So what you do, you are taking the parameters of atom type A, atom type B, and you just combine them using some simple rule. So for example, either the geometric mean or arithmetic mean for sigma and epsilon parameters. And for water and hydrogen, from the previous examples, it looks like this, that you have this sigma epsilon for water, this sigma epsilon for hydrogen, this sigma epsilon for oxygen, and you are just averaging them and get the parameters for interaction between oxygen and hydrogen. And the bad part is that these rules are different for different packages and different force fields. Again, this is not compatible. Of course, there is much, much more. So in addition to the atomistic MD, you have also coarse-grained MD, where you combine particles together to larger, let's say, quasi-particles. You have non-equilibrium MD, you have external potential, you have hybrid techniques with QM and MD. You have multiple enhanced sampling schemes, ML potential, multiple time stepping, and so on and so forth. So you really need several years to understand briefly what's going on in this domain, but on practice, you just need a subset of this. So it's not as severe if you really don't need to dive deep into this technique. And at the end, I will show you some applications of MD in drug discovery. So first thing is protein structure prediction. So we are speaking about AlphaFold several days already. So we have X-ray, we have cryo-EM, we have AlphaFold. But all these structures are not native. So cryo-EM or X-ray structures are not in the solution in the room temperature by any means. So you're getting something, but you don't know how it relates to the functional form of your protein. And one of the ways how to study this, you can relax and assess the stability of this protein in the native environment using MD. For AlphaFold, it's also the same story. So AlphaFold predicts something, but inside the AlphaFold, there is an MD-like minimization on the very last stage of the AlphaFold operation. They use Umbra force field to minimize the clashes. If you don't do this, you will get the model where actually amino acids are clashing with each other. And in order to get rid of this, they are using MD. So it's kind of cheating. They call it AI model. It's not AI model. It's AI plus MD. So it's used to coordinate generation to remove the clashes. And for example, you can see how it works in terms of refinement of the cryo-EM structures. For example, you can use multiple MD techniques to go from the coarse-grained cryo-EM map to the atomistic representation, and you can put into the place misplaced amino acids, for example. Another thing is generating ensemble of conformations for virtual screening. So again, if you have X-ray or cryo-EM, it almost never matches the exact conformation in the cell. And this is one conformation, and the protein is dynamic. It shakes all the time. It changes from one conformation to the other. And with MD, you can sample this. So you can obtain the set of representative dynamic structures, which are close to real conformations. And after that, when you are doing virtual screening, for example, you can do the ensemble screening, not to one conformation, but let's say to 10 representative structures in different forms and conformations. And after you did your docking, you can also do another round of MD to assess the quality of this docking pose, if it is stable in dynamics or not. Because if you dock your compound to a particular conformation and then the conformation changed, the molecule may just detach easily. And this will get you understanding how stable is it, and also the correctness of your docking pose. Another thing, if you're working with peptides, not with the small molecules, we have a huge pain with the peptide conformations. So basically, in the solution, peptide conformations look like this. So it's kind of spaghetti, it's very dynamic. And when you want to bind your peptide to the protein, it's usually some predefined conformation. And you don't really know which one unless you have some crystal structure or another kind of prediction. And this flexibility is a problem for conventional techniques. In order to reduce this, people are using cyclopeptides, because one of the leading causes why people use cyclopeptides is to tame a little bit this flexibility, to link it into the cycles, to limit the flexibility of the backbone dihedrals. And using MD, you can sample these conformations, and you can choose those which are mostly relevant and most abundant, either in the solution or in complex with the protein. And after that, you can work with this. Another thing is free energy perturbation, which is the mostly used on the later stages of drug discovery for lead optimization. And the idea is that on this stage, the compounds become very complex and very expensive. Synthesis of each new compound, which is supposed to be better than the previous one, may cost $100,000. And you need some rational technique to select which compounds to synthesize. And FAP is this technique because it provides you the binding free energy of your ligand with a protein with high precision. Actually, what you are computing is not the absolute free energy, it's a difference in free energy between several compounds, which differ a little bit one from the other, let's say by substitution of few atoms or some chemical group. And it works in terms of alchemical mutations. So you are changing the topology of your molecule. That's what I mentioned when I say that you are playing the god. So you as a god, you just alchemically mutate one molecule to the other, and you see how the binding energy changes. It works the best with a series of similar compounds, and that's why it's used on the lead optimization stage, but this is very resource intensive and also very fragile in terms of the setup. It's usually painful to set up, so you don't want to do this in the early stages. And the idea is how it works. It's like this. So you have your compound A and your compound B. You have them in water, and after that you have them in complex with a protein, bone to protein. And what you want to compute is the energy of transferring it from water to the bone form. So this delta G of binding for ligand A and ligand B. But you cannot do this easily. And instead of doing this, you are doing what is called the thermodynamic cycles, because your interaction functions in MD are potential functions, which means that the function doesn't depend on the path, how you connect one conformation of the system with the other. You can directly go from A to B, or you can go from A to C, to D, to E, and after that arrive to B. And the energy of this cycle would be exactly the same. This is a definition of potential functions. And because of this, in order to determine the difference between delta G A and delta G B, what you can compute, you can compute the pass from here to here, so mutating compound in water from A to B, and then from here to here, mutating compound bound to the protein from A to B. And by subtracting this one from this one is the same as subtraction of this one to this one. So you are cheating, and in this way you are getting the delta G of binding between two compounds. And in practice it looks like this, and this kind of scary map is mutations from one chemical species to the other in the optimization pathway. So you have your parent compound, I don't even sure which one is parent here, it's not so obvious. Let's say this one, and after that you are trying different substitutions, and you are computing all the differences in binding energies between these species, and you are finding the best one. And after that, this best one can be synthesized and used in the experimental screening. So, the conclusion. The MD is a very large field in life sciences, and it becomes really kind of separate discipline by its own. You can spend years working with MD like I did, so I'm doing this for more than 25 years for now. And it had multiple applications in drug discovery in many related fields, and at least understanding of its capabilities, its limitations, is critical to build a successful career in drug discovery in both academia and industry, because it's used everywhere. And what is important, that reading the tutorial doesn't make you an MD expert. This is something to take out. So practical hand-on experience is always required to feel how it works. And as I said, it's a large field, so always question what you did and always consult with people who are experienced with this, because there are many, many pitfalls if you are using this in practice. And say this, thank you for your attention. Questions?
What are your thoughts about attempts to replace the integration in MD by artificial intelligence?
Well, there are two things. First, you can replace the integration in a way that you are generating confirmations without integrating motion equations. That's what I mentioned briefly yesterday, that there are a bunch of techniques of doing this. It's possible, but after that, the confirmations you get, again, you have no feeling how real they are. So typically, on top of these confirmations, people are running short MD runs to understand if it is stable, at least. It's possible. Another thing is MD potentials, because these empirical potential functions with a lot of parameters are kind of low-hanging fruits for ML techniques. So you can use existing MD simulations, or you can just run simulation of small molecules of different kind, and after that use ML to derive the empirical equations for you. This is another thing. This is a very active field now, but I didn't see real applications of MD-derived force fields in industry so far. At least publicly, nobody uses this in production, so this is kind of development techniques. Any other questions?
Also, you mentioned that it might be possible to model reactions with MD, but it's still kind of a niche field, so can you elaborate a bit on that?
Yes, so there is a force field which is called ReactFF, which is designed like 15 to 20 years ago exactly to model the reactions. And it works in such a way that instead of the harmonic potential between the atoms, which describes a bond, you have the realistic potential which goes like this to infinity, and you can actually break the bond. The problem is that the parameters are quite hard to get for this kind of potentials, and they are much, much slower in terms of computational intensity. because this is not just a harmonic potential, this is complex functional form. And you also need to treat specially the electrostatic interactions because you have to go beyond the cutoff and all the things like this. So there are some works which use this reactive FEV, but this is not very popular. So this is really a niche theme. If you need it, then most likely you will use QM for this.
What do you think about the simulations of short linear peptides? Because sometimes when we perform docking operations with protein-protein interactions, we have, a short peptide that is alpha helix or beta sheet, so it is structured. But when we perform MND simulations, it often occurs, at least in my case, that they are, unstructured. So, do you think there is a force field better than another to deal with this problem?
Yeah, you see, for peptides, I would say all the modern force fields are roughly the same. There is no difference. Some of them are kind of exaggerating helicity, as far as I know, but not to the extent that you will see the difference between helical and disordered. All of them are giving pretty much the same results. And with peptides, the most challenging part is to understand what is the conformation in the complex. Because in solution, you can get whatever you want, but after the binding, it can unwind or it can form the secondary structure. And this is really a problem. So you need some kind of initial guess, in a way, how it looks like in the complex. And if you have interactions, a protein-protein interaction, for example, you can look at the other partner protein and see what is the, if it is a loop or some other kind of other protein which is in contact with your protein of interest, and model your peptide, at least a backbone conformation. According to this, that's how we usually do this, because without initial guess, there is a whole field of possibilities. It's not tractable.
So, thank you for your talk. I have a question about the explicit model oscillation. Does the model oscillation you actually choose really influence the outcome of the MD, or it doesn't matter at all?
Yeah, it's a very good question. It depends what you want to achieve. So, for example, if you're interested in the protein conformation on the long run, like microseconds, that I would say it's pretty much doesn't matter which water molecule model you use, if you use something decent, something recommended for the force field. If you study something very sensitive to the details of water interaction with a molecule, like, for example, radial distribution functions, which you can compare with either X-ray or neutron scattering, then it becomes very important. Because a wrong water model will give you absolutely wrong results in terms of these subtle things. So it really depends. And there are water models which are designed for this kind of subtle effects.
Is there any specific one you would recommend for basic drug design?
Again, depends on what you want to do. So if you can tell me what you want to achieve, one or the other could be better. But usually, if you are using something like OPC or TIP4P model, it's usually okay. But it's universally recognized that, for example, TIP3P, which is default for the charm force field, is bad. It's okay for biological contacts in the normal conditions, but looking at the water properties, like the temperature of crystallization or evaporation or density changes, when the temperature changes, it's absolutely off. So it's fine in the narrow domain near the room temperatures. So it's better to use something else, but other than that, all of them are, let's say, okay.
If I may add to this question, one important parameter which is quite specific towards the individual water models is the diffusion.
Yeah.
So if you are looking into a property which is important for the diffusion, like if you are studying how the molecule that case, the water model is quite crucial. You have to have this diffusion right in that sense. If you want to compare to the experimental lab as well. But in general, if you just want to see the structure of the protein and you are just running short simulations, then the water model is not that important. But if you are studying anything about the transfer properties, then it's at least worthwhile to try several models and check which one is most compatible with the experiment you have in hand.
Yeah, and you should really compare with experiments. If you're really working with these subtle things like kinetics of water binding, because most of the time you don't need to do this.
Maybe a quick follow-up to actually this idea of replacing integration with artificial intelligence. So is it actively explored?
Yeah, it's very active field. So there are those.
How does it actually work? Is it like the model predicts the next frame in the simulation, or?
Yeah, as I said, there are two kinds of techniques. You are either generating conformations, which is not really predicting the next step. It's predicting which conformation you may have in the ensemble at some point of time, not necessarily the next time step. Because the reason, if you dive a little bit into the physics, the reason why you are doing the trajectory, why you are integrating, because you have the ergodicity hypothesis. So if you're integrating long enough, you are getting the distribution of states which corresponds to the Boltzmann distribution. But if you are in the equilibrium, you don't need to go from one conformation to another in terms of integration. If you can predict the ensemble, it's fine. If you have the ensemble, you have everything. And MD is actually, ML trying to do exactly this, just to avoid integration and to deduce the correct ensemble in one shot. This is one set of techniques. And another set of techniques is, okay, we will do integration, but the potential we will determine not from QM or from the wild guesses, but from ML. Okay.
So if there are no further questions, then let me thank and now we will have a coffee break, and at the beginning of coffee break we will grab the opportunity and make a photo.
Thank you, first of all, and thank you for the invitation and the opportunity to present some of the work we have been doing. So there was an Italian educator, Gianni Rodari, and he was quoted as to say that a lesson in which laughter has not been heard is a wasted lesson. So the first goal is to try to make some of you laugh at least part of the time, although this is a serious issue. I already see some smiles, so I'm doing a good job. There is going to be a bit of overlap with the previous lecture, not much, and I hope I will be able to highlight some other stuff. So I'm going to talk about cystic fibrosis. And cystic fibrosis is the most commonly inherited disease among Caucasian or people of European descendants. The number of CF patients is estimated anywhere between 60,000 and 160,000. In Israel, where I come from, there are about 700 CF patients. And CF causes many pathologies in the human body, but it affects primarily the lungs. And most CF patients die from lung failure. So what you see here on the left, maybe it will be easier with this. There is a pointer. Oh. No. There should be, here. Okay. Yeah, right. So what you see here on the left is the lung or the airways of a normal individual, and what you see here on the right is the airway of a CF patient, which is completely obstructed by sticky mucus, and I'll get in a second to why they have sticky mucus. And then if you go over here, so in 2008, the median survival age of CF patient was only 26 years. Today, it is estimated that CF patients who were born in 2022, and they get treatment from pretty much day one, they will live up to 66 years. And this is a huge increase in life expectancy. Now, CF is caused by mutation to a certain protein. It's called cystic fibrosis transmembrane conductance regulator, CFTR for short, and we're going to use the short version of it. So what is CFTR? It's a member of the ABC transporter superfamily, and this is one of the largest and most ancient protein family in the human body. It contains 48, in human, it contains 48 transporter. These are all membrane proteins. And there are two types of transporters, importers and exporters. So importers brings nutrition and stuff into the cell. Exporters take compounds out of the cell. And in human, there are only exporters. Does anyone here ever heard about P-glycoprotein? Okay, so P-glycoprotein is one of the most known exporters, and it is expressed in cancer cells. So the way a cancer cell protects itself against chemotherapy is by overexpressing PGP, and PGP just take all the chemotherapeutic agent which you try to put into the cell and pumps them out. So this is a classical exporter. And as I said, in human, there are only exporters. So what's so unique about CFTR? It's an ABC transporter like other ABC transporter, but it is the only ABC transporter known to function as an ion channel. Specifically, this is a chloride channel, and the structure is shown here. So it is made from two transmembrane domains, and the chloride pathway is roughly in this region, and these are connected by these what are known as intracellular loop to two nucleotide binding domain. The role of this nucleotide binding domain is to hydrolyze, to attach, to bind, and to hydrolyze two molecules of ATP. And when the two molecules of ATP are bounding into these two NBDs, the NBDs dimerize, the channel opens. Upon dissociation of ATP to ADP, the dimer dissociate and the channel closes. What you see here is an unstructured part of CFTR, which is called the R domain. We'll get to it in a second. And over here in triangle, this is the site of the most common CF-causing mutation. It appears in about 60% of CF patients, and it is a very severe CF-causing mutation. We'll get to it in a second. Some historic perspective. So the gene of the CFTR was first cloned about 35 years ago in 1989. The first low structure of CFTR came about in 2004. It was so low resolution that you basically couldn't see anything. And then in 2008 came the first homology model of CFTR, and from that on, other homology models came about, but the first structure, experimental structure of CFTR came about in 2016. It was on December 2016. The reason I remember this is the day before it came about, the day after it came out, I was supposed to give a lecture on CFTR. And in the evening, I found that there is a news at the first structure of CFTR, so I had to modify my entire lecture. This is a cryo-EM structure. Until now, there is no crystal structure of CFTR. This is a membrane protein. It is completely unstable outside of the membrane, and no one was able to crystallize it until now. Okay, so CFTR, sorry, I'm going back to here, just to show you the obvious that CFTR has 5 domains, 2 transmembrane domains, 2 NBDs, and 1 R domain. And the folding process of CFTR is pretty complex. So protein can fold either co-translationally, that is, together with the translation process, they already fold, or post-translationally. The translation process is over, and then they fold. CFTR is not that unique, but it uses a combination of post-translational and co-translational folding. So the basic 3D arrangement, kind of a loose folding, is done co-translationally, but the final folding into a real compact and functioning CFTR is done post-translationally. And this F508 del mutation, the deletion of a single residue from the sequence at position 508, basically kills the post-translational process. So F508 del CFTR does not fold properly and does not make its way to the cell membrane. We'll see the consequences of this in a second. Now, CFTL is an ion channel. Ion channel gate. Gating means they open and close. So here's the gating cycle of CFTR. So this is the resting state of CFTR. These are the two NBDs. These are the two transmembrane domain. These are the two NBDs. And this is this R domain, which, as I said, is largely unstructured. So even in the cryo-EM structure, you don't see this part, but we know it is there. So initially, this R domain sits between the two NBDs. When it is phosphorylated, it leaves its initial position, moves away, and as a result, the two NBDs can now bind two molecules of ATP. Upon ATP binding, they form a head-to-tail dimer. Basically, they dimerize, and the channel opens. And upon channel opening, chloride ion can pass. Now, when a single ATP molecule, that which binds to NBD1, dissociate, the channel closes and gets back to its resting position. And sometimes the R domain goes back and then goes back to in between the NBDs, and we get back to this stage. So, given that, you see that CFTR has many, many conformations along its gating cycle, and some of them, perhaps all of them, can be of clinical importance. Now, CFTR mutations. So CFTR has over 2,000 known mutations. Not all of them were tested to make sure that they cause CF, but about 700 were, and from those that were tested, about 720 are known to be CF causing, and only 25 mutations are known to be non-CF causing. And the mutation can operate in different mechanisms, but they all have one thing in common. They all compromise the ability of CFTR to conduct chloride ion across the cell membrane, either because the protein is not generated in enough quantities, or because it does not fold properly, or because it doesn't gate properly, or because it doesn't conduct, or because it is unstable in the cell membrane. But again, no matter why, CFTR with mutation does not properly conduct chloride ion. So why do we care about this? So I'm going to show you this movie in a second, but the idea is the following. Your epithelial lung cells are covered with mucus. And this is a good thing because the mucus protects the cells. However, the mucus should be hydrated because as long as it is hydrated, it can be easily cleared from the body. And on the cells, there are small organelles which are called cilia. And these cilia are making this type of movement, and in doing so, they are constantly removing the mucus outside of the body. Now, this mucus layer should be hydrated. When chloride ion is passing from within the cell towards the outside, it carries with it, because of the osmotic pressure, water molecules. And these water molecules keep the mucus layer hydrated, and then it could be easily cleared from the body. However, when CFTR is not functioning, chloride is not moving, water molecules are not moving, the mucus layer gets dehydrated. Once it gets dehydrated, it is being colonized by bacteria, which leads to lung function, and then chronic lung function, lung dysfunction, and eventually death. So let's see if this works. Yeah, it does. So here's a tour into the lung. We're going to turn left in a second, into the airways. I'll move this. So these are the cilia. This is the mucus layer in green. The cilia is beating, the mucus layer is being removed from the cell, which is good. CFTR is functioning. So this is CFTR. Chloride ions are moving through the channel. Water molecules are moving through the membrane. The mucus layer is hydrated, and everything is fine. Now, in a second, we'll see that CFTR is not working. You see the chloride ions are not moving to the other side. As a result, water molecules are not moving through the membrane. As a result, the mucus layer gets dehydrated. The cilia are no longer able to remove it. The mucus layer sits on the cilia, depresses them, and these black points are colonies of bacteria, which populate the mucus layer, hence infection. Okay, so given that, what is the treatment hypothesis? So ion conductance depends on two factors: the number of ion channels in the membrane and the time they stay open, because an ion could be conducted just when the channel is open. So given that, the current is kind of a multiplication of the number of the channel times the open probability. So CFTR correctors are compounds which attach to the CR, correct the folding defect, and bring more CFTR channels to the cell membranes. Potentiators increase the open probability of those channels which are already at the cell membrane. And kind of people were thinking for many years about this kind of magic bullet, something a single compound which will do both. Nobody found it yet, so most CFTR therapies are actually combo therapies. They are made of potentiators and correctors. So here's an example. So another nice movie. So why is this not working? That's strange. It worked like 2 minutes ago. Can anyone suggest how to make this work? When I tried it before, it has this line over here. Okay. Great, thanks. So this is CFTR. This is a corrector, a small change, and then CFTR is working. Okay. So here are the known CFTR therapies. So there are four compounds. 3 of them are correctors. The one on the right is ivacaftor. This is a potentiator. Ivacaftor was the first compound which was developed by Vertex as a drug to treat CF. 2 things about it. CF cannot be cured. There is no single person who can say, I had CF and now I don't have it anymore. But it could be modified in the sense that people with CF using this drug can live long and good life. People now are talking about mutation-agnostic therapy, CRISPR, gene therapy, and so on. Didn't happen until now. Another important thing which was brought to my attention yesterday is that all these compounds were developed with no computational help at all. These are classical medicinal chemistry lead optimization projects. The structure of CFTR came about long after these compounds were developed. Okay, so you see there are 4 compounds, there are different combinations, there is several combinations, one combination of 3 compounds, and again, they allow CF patients to live long and reasonably good life. This is another compound. Now, you may wonder why this didn't find its way to the table, because this was approved only about a month ago, and I was too lazy to put it into the table. But this is the latest CF therapy which was approved by the FDA on December 2024. This is the same compound, by the way. Sorry, So this is the same compound as I showed you before. The only difference is that the hydrogen were replaced by deuterium. Turns out that this makes the compound more stable. So this compound could be taken once daily instead of 3 times daily. And for CF patients, this is a huge improvement. Okay, some structural information. So back in 2004, the first structure of NBD1 appeared in a paper by SGX, and it contains 6 structures. Today we have about 36 structures with better resolution, and we're talking now about NBD1, only about NBD1. The first nucleotide binding domain. This was the first domain of CFTR which was ever crystallized. And I told you that there were not, until 2016, there were no cryo-EM structure or crystal structure of the full-length protein. There were models. There were, because CFTR has several conformations along its gating cycle, it was modeled based on different templates. And I'm showing you only 5 models out of maybe 20 which came about. And as I said, in 2016, the first cryo-EM structure came about, and today we have about 30 different cryo-EM structure of CFTR, different states, different modulators, and most of them are wild type. One of them is with the F508del mutation. I think that almost all structure came from the same lab. Jude Chang lab at Rockefeller University, all are cryo-EM structure, and all the papers were Science, Nature, Nature Communication, all the great journals. Some of the structures show the CFTR pore. So here on the left-hand side, this is a CFTR in the unconducting state, and you can see that the pore is closed over here. This is a CFTR in the conducting state, and this is the ion channel which opened through the extracellular region. So this is a closed conformation of CFTR, and this is an open conformation of CFTR, and all these structures are excellent points for MD simulations. So, a little bit about MD simulation. This is a force field. By now you know what a force field here is. But how many Schrödinger equations are you aware of? How many Schrödinger equations do you know? 1, 2, 5, 6. Come on, guys. Only one, right? There is only one Schrödinger equation. The reason is that there is a basic physical truth behind Schrödinger equation, okay? There is absolutely no physical truth about force field. Force fields are empirical creature. Each one of you is completely free to develop his or her own force field. There is no such thing as a correct force field or a wrong force field. There is only a useful force field and an unuseful force field. A useful force field can reproduce experimental data and hence can be used to predict something you never tried before. An unuseful force field is simply unable to reproduce experimental data, so you cannot use it. Now, a force field will generate a potential energy surface for each molecule. Each force field will generate for each molecule a unique potential energy surface. If you want to do any calculation, if you want to compare experiment with calculation, you need to sample this potential energy surface. And there are several ways to do it. The easiest way and the worst way is do energy minimization. Why is it easy? Because this is just energy minimization. Why is it bad? Because this sampling is completely unconverged. It completely depends on your starting point. You start from one point, you get one structure. You start from another point, you get another structure, okay? Another way which partially solves this problem is what is known as conformational search. And if you do it properly, and between you and me, there is no way to do it properly on a very large protein, but let's assume there was a way to do it, you get all minima, okay? The point is that in order for a structure to get from this minimum to this minimum, it needs to also be in this point, and this point, this point, and this point, and that point. And conformational search will only find minima. It will not find all the points between them. So if you really want to sample correctly your potential energy surface, you need to do MD simulation. And again, last talk we heard about MD simulation. I'm not going to describe the method anymore, but I will say something about the challenges of MD simulation. Okay, so the first challenge is what is known as the sampling problem. MD simulations are notoriously slow to cross energy barriers. Here is a very simple example. Now, I did this example about 20 years ago or 30 years ago when I was doing my postdoc. So the numbers are probably not correct because the computer has evolved, but the idea is still the same. So this is a very simple system, cyclohexane. Okay? It has two conformations, methyl cyclohexane, axial and equatorial. The energy difference between them is about 1.7 kcal per mole. The barrier to interconverting between them is about 10 kcal per mole. If you start a standard MD simulation from the axial conformation, it will probably never go to the equatorial one unless you use specialized method. So At one point, again, 30 years ago, I made a calculation that it would took this system to converge about 40 years. Today, it could be done much faster, but 40 years. So over here on the left-hand side, this is Moses taking the people of Israel out of Egypt. And it is not well recognized in the Bible, but his stretch hand over here, he was actually starting an MD simulation. And then he took the people of Israel to wander in the desert for 40 years. This is according to the Bible. And when they go to the Holy Land, the simulation ended. Okay, it's not 40 years now, but again, this is a problem, okay? MD simulations are very slow to converge. One way to overcome this is replica exchange. There are other ways. The reason I'm mentioning replica exchange is because we use it, and I'll show it in a second. Replica exchange, you are running multiple replica of the same system at different temperatures. And because you are running at higher and higher and higher temperature, you increase the probability of crossing energy barriers. And now you take all the trajectories and you combine them together and you get a much better convergence than what you would get if you are running at one standard, say 300K or 300K degrees. Okay? It's very easy to set up. It's very nice. There is only one problem. Replica exchange works on exchanging using a Monte Carlo experiment or Monte Carlo test between two temperatures. So the temperature range, so the difference in temperature between the two simulations should be rather small. If it is too big, you are not going to get any changes between this replica. Now, if you want to span a large temperature range, you need to run many replica, and this is beginning to be tedious, okay? But this is, leaving this aside, this is a nice and a rather intuitive method. Now, how do you analyze your MD simulation? The first thing you must remember is always look at the result. Always look at the trajectory, okay? Never just rely on numbers. Numbers are great, but they don't convey the full picture. Take your trajectory, upload it to VMD, whichever software you like, I don't care. But stare off it for half an hour, try to understand what you do there. Can anyone guess, based on this picture, what this is all about here on the right-hand side? I always look on the, no? Come on, guys. I'm not going to play it all the way. But just that you get a feeling. See, people are smiling. Okay. You want to hear it all the way to the end? This is Life of Brian, Monty Python. Anyone who didn't see it, this is a must. Okay. Okay. If anyone is interested, I can send you the YouTube. So we're still in the MD simulation analysis part. RMSD, that's the first thing you're going to look at, RMSD plot. You're superposing all your trajectory onto a reference structure, and you look on how it evolves in time. Now, people sometimes say that RMSD is a measure of stability. This is not completely correct. When you will always see or almost always see an increase in RMSD of a protein. Because if you start from a crystal structure and then you're moving a protein into a solvent environment, as we've heard in the last talk, the structure is going to change. The structure is going to leave the crystal coordinate and evolve with time. What you want to see is something like this. You want to see kind of convergent, and it is perfectly fine to have some fluctuation because they represent the different conformational state of your protein. What is not good is if you see something like this. If you see something like this may suggest that your protein is disintegrating during the simulation. However, if you have two proteins, a wild type and a mutant, and the mutant is slightly higher RMSD-wise than the protein, but they both converge, you cannot deduce that the mutant is less stable. It only means that it moved a little far away from its initial position than the wild type. That's all. What can be sometimes correlated with stability is what is known as RMSF plot. RMSF, root mean square fluctuation. So in this graph, you have on the x-axis the residue number, on the y-axis the amount to which it fluctuates. The higher it fluctuates, the more, or there is in certain cases, and I'm going to show you one example, there are correlation between the degree of fluctuation and the degree of thermal stability, okay? Another thing you can look is correlation matrices. Correlation matrices basically tell you which part of the protein move together, which residues are correlated with which residue. This is important because many protein, and CFTR is one of them, are allosteric. Everyone knows what allostericity is, right? You do something here and something happens there. And looking at these covariance matrices gives you a good feeling of which part of the simulation of the protein, are correlated with which other parts. Another thing which you can do is look at the principal component analysis, and there are two things you can do there. Here on the left-hand side, you see the part of space which was covered, say, by a wild-type protein, which is in black, and a mutant protein, which is in red. So in this case, you see that the wild-type protein covered larger part of the conformational space. This might be the reason why the wild type behaves in a certain way, and while the mutant behaves in a completely different way, okay? In this case, the mutant covered a smaller part of the space. And finally, this is what is known as a porcupine plot. And the porcupine plot gives you a feeling of the general movement of the protein. And you see the arrows here. So these arrows, it's a little bit hard to see, but these arrows here point in this direction, and these arrows here point in this direction. So this protein is making this kind of movement, okay? And sometimes this kind of movement tells you something about what the protein kind of wants to do. So these are important things to look at. Okay, so this was a very brief introduction to how to analyze MD trajectories. This is NBD1, the first domain of CFTR we worked on. The reason is that we had crystal structure already in 2004, so we had good starting point for our simulation. It is made of like 5 or 6 domains. It binds ATP, so this is the ATP binding part of NBD1. The first thing we ever do is run MD simulation, replica exchange MD simulation on NBD1, wild-type NBD1 in blue, and F508 NBD1 in red. We also had a crystal structure of F508del NBD1. You see that the red lines, these are RMSF profile, you see that the red lines are always above the blue lines, which means F508del fluctuate to a higher degree. Another thing which you see here is that each simulation was repeated several times. And this is, again, an important take-home message. Never, ever report results from a single MD simulation. Repeat the simulation 2 times, 3 times, 4 times, a few times, and if you want to report something, report the result of the individual simulation and average values, but never, ever report anything from a single simulation. So in this case, we repeated each simulation 5 or 6 times, and indeed, the wild type is thermally more stable than the F508del by about 6 degrees. And this was reflected in the RMSF. Now, you see that one of the places where the largest difference in RMSF is in this region. And this region is indeed the region of the mutation. The deletion of F508 happens in this region. We then extended this simulation to F508del in the presence of a known corrector. This is not a clinical candidate. This is a very small molecule, a very weak corrector. Nevertheless, it stabilizes NBD1. And you see that this is reflected in the RMSF profiles. So the red, is F508del without the corrector. The green is the F508del with the corrector. And here is a comparison between wild type and F508del in the presence of the corrector. And you see that the RMSF plot not completely, but reasonably well coincide. And then we did the same trick for several other mutations, and we got actually pretty nice correlations between thermal stability and RMSF profiles for 5 or 6 different constructs, which was nice. But this simulation takes time. So we want to see whether we can do something which is kind of quick and dirty. So the idea was to look at protein stability. So we had a data set of about, 30 mutations with experimental thermal stability data from our collaborator. And we wanted to see whether we can reproduce them with any of the tools which are supposed to give delta G free energy difference between a wild type and a mutant protein. So we tried, I think, 14 different tools, and the best results were obtained with Foldex. Okay? The best results were obtained with Foldex. The second best results were obtained with Rosetta. But these 2 tools are supposed to give delta G difference between a wild type and a mutant. Here are the correlations which we obtained with Foldex. They are not great, but they're actually not that bad. One of the reasons we did it is we said the following. If we actually are able to get good correlation, let's look at what makes up the force field which Foldex uses. And using this information, perhaps we could understand what causes a mutation to be destabilizing and what causes a mutation to be stabilizing. So by doing this analysis, we got to the conclusion that stabilizing mutation overall, on average, benefit from better hydrogen bonding, whereas destabilizing mutation, again, overall, on average, suffer from steric clashes, which is probably not that surprising. Okay, so this is nice, and we can easily do it, in a matter of hours on many, many mutations, but this doesn't provide us too much mechanistic information. So we went back to MD simulation. And in this case, we wanted to do something else. Rather than running a simulation at 310 or 300K, the usual temperature, we wanted to see what's going to happen if we increase the temperature. And the assumption was that a stabilizing mutation will resist temperature increase more than a destabilizing mutation. So we look at 6 constructs, wild type, G551D, which is a neutral mutation. This is a CF-causing mutation, but in terms of protein stability, it is neutral. That is, a protein with a G551D mutation makes its way to the cell membrane. The only problem there is that it doesn't gate properly. And ivacaftor, the first molecule which I showed you, actually was designed to solve this problem. And then we look at 2 CF-causing mutations, these 2, which reduce the thermal stability by this amount and this amount. And as a control, we look at 2 stabilizing mutations. Now, we wanted to look at 2 stabilizing single mutations, but unfortunately, there is no single stabilizing mutation which increases the stability of NBD1 by a reasonable amount of degrees. And because this was our first attempt, we wanted to look at effects which are more obvious. So we look at sets of mutations. So these 6 mutations together increase the stability of CFTR, of NBD1 by 17 degrees, and these 4 mutations together increases by 9 degrees. So this is kind of comparable to this decrease, okay? And we wanted to see whether if we run MD simulation and analyze the trajectories in many ways, can we find a single or maybe multiple parameters which correlate with the experimental findings. So I'm going to tell you from the start. We found it, but not for G551D. G551D, no matter what we did, we simply are unable to correlate it with the experimental result with the mutation. With the MD simulation. In MD simulation, this mutation behaves as destabilizing, and we really don't know why. But let's leave it at that. So this is the protocol. And it's complex, and it's not that important. We started, but these are long simulation. So we heated the simulation until 410 for 200 nanosecond, and then we continue it at that elevated temperature for another 1.6 microsecond. So all in all, 1.8 microsecond, and each simulation was repeated 3 times. Why 410? Because when we tried other temperature, we didn't get a very good correlation with experimental data. Why 1.8? I haven't got a clue. It just looks like a nice number. And at one point, we got tired. Okay, so here are the RMSD. So the vertical lines here are, this is the end of the heating, and after 900 nanosecond, give or take, we observed some convergence. Now, this is not perfect convergence, and you see it for the wild type, okay? The blue one. So this basically tells us that even after we stopped heating and continue running at 410, the protein still disintegrates. Okay, it actually makes sense. So these are the 2 stabilizing mutation. These are the 2 destabilizing mutation. This one here is G551D, which is always an outlier, and this is wild type. As I told you before, this does not tell us that these are indeed more stabilizing mutation. Okay? It just tells us that this departed to a smaller extent than, from the initial structure than this one, although you do see that these simulation here have larger fluctuations in RMSD. These are the RMSF profiles. This is for the destabilizing mutation, and this is for the stabilizing mutation. And here it gets interesting. So this is wild type in blue, and the 2 destabilizing mutation indeed have higher RMSF profile. I'm showing here average values over 3 simulation. And this is, again, the wild type in blue, and these are the 2 stabilizing mutation, which, again, have lower RMSF profile. So this kind of echoes what I showed you before. In this system, there is correlation between RMSF profiles and thermal stability data. And this is something which I actually like. DSSP. DSSP is a method to look at secondary structure. So you know that the secondary structure of protein is defined by the torsional angle of the backbone, right? There are 2 main structure, alpha helices and beta sheet, but there are also loops and disorder and so on and so forth. So DSSP basically tells you which structure of the protein the protein is in based on the torsional angle. So this is the wild type protein. And if you look at this region over here, red is alpha helices. So you see that the wild type is this is the Y, on the x-axis is the simulation time. The y-axis is the residue number, which is a little bit difficult to see, but it's not that important. So you see that, for example, these 2 parts over here and over here in the wild type protein are maintained until, I don't know, 900 nanosecond, maybe microsecond. But if you look at these 2 destabilizing mutation over here and over here, the alpha helix breaks down much, much earlier. And if you look at the stabilizing mutation over here and here, the alpha helix is maintained throughout the rest of the simulation. And again, G551D looks like destabilizing, although we know experimentally that this is a neutral mutation. So this is actually interesting because first of all, it tells us that indeed the mutant construct loses alpha helicity, and they are doing it pretty early during the simulation, also after the heating phase. Okay, so when they're run at 410, they are disintegrating. We also look at the fraction of native contact, and we saw the similar trend. So this is wild type. This is the 2 stabilizing mutation, which lose a smaller fraction of the native contact and seems to converge. The wild type continues to disintegrate. And these are over here, these are the 2 destabilizing mutations, which lose a larger fraction of the native contacts. And again, this is G551D. So many of the computational matrices which I showed you correlate pretty nice with the thermal stability. And we can also get some mechanistic information, because if we are looking at the DSSP, we can see which residue are the first to disintegrate. And given that, so in this case, so in this mutation, the LR67P, this integration happens here, but also to a certain extent to this region. Whereas in this mutation, all the disintegration happens here. Now, I forgot to tell you, these two mutations are CF-causing mutation. They are severe CF-causing mutation, pretty rare, not many patients with this mutation. So this can suggest to us that perhaps if we stabilize this region over here using maybe small ligand, then perhaps we are able to develop, I don't know, mutation-specific therapies for CF. But this is a long way ahead of us. We can also, if we are looking at the time at the DSSP over time, we can actually see which region disintegrate first. So in one of the mutation in the L467P, this region starts to disintegrate after 285 nanoseconds, followed by this region after 355. And in this mutation, these two regions start at 240 and then after 310 nanoseconds. Okay? So this is just a time evolution of the disintegration. Binding site of NBD1, I just told you that perhaps we are able to stabilize NBD1 by binding ligands to it. So people have looked at it in the past, and these are the binding site that people found on NBD1 in the past. So this is the ATP binding site. Why is it important? Because one of the mutation, L467P, resides in the vicinity of NBD1. Now, people have shown in the past that if you bind ATP analogs into NBD1, you are able to stabilize it, which is nice. Now, another mutation, this A559 mutation, is located roughly in this region. You remember this BIA? BIA is a small corrector, which I showed you before, which stabilizes NBD1, and it also binds in this region. And this region is called F5OL ICL4 region, and so perhaps binding a molecule, small molecule, to this region could perhaps ameliorate the effect of this mutation. And this part here is also interesting. So people were able to, NMR studies show that this small corrector binds to this region over here. The problem is that if you look at the structure of NBD1 crystal structure, you are not going to find any binding site there. Okay, it's completely blocked. However, when you're doing MD simulation, a binding site opens in this region. And so, and in this case, NMR experiments show that the molecule binds to here. There is no site in the crystal structure. MD simulation opens up a site, and this is our docking of this compound into this site. Okay? So this is another important take-home message. Crystal structure are only snapshots. They are not the real world. If you want to get a better feeling of the real world, run MD simulation. Okay? Okay. You've already seen this slide. I'm just rehearsing the fact that all these structures are excellent starting point for MD simulation on full-length protein. And I'll give you just a few examples. So this is the first attempt we did. This is no simulation here. But a clinician from one of the hospitals in Israel approached me, and they told me, look, we know that these two, this double mutation, they are always occurring together in a Jewish patient from Georgian descent. Can you try to explain to us what this mutation is doing? So in this mutation, you see that Q is replaced by lysine, and threonine is also replaced by lysine. Now remember, CFTR is a chloride channel. Chloride is negatively charged. In this case, you are taking two neutral amino acids and changing them into amino acids which might be positively charged under physiological pH. If you look at the model, you see that these two mutations or these two residues point into the channel. So you're generating a positive charge along a pathway of something which should be negatively charged. So no wonder, or I know, no wonder, maybe it's a strong word, but we can certainly hypothesize that this generates kind of an electrostatic trap which slows the passage of chloride ion in this channel. This is a hypothesis. We never tested this by simulation. Today we can do it. I'll show you in a second how. But These are MD simulation of full-length CFTR. And these are kind of sanity check simulation. Why sanity check? We ran simulation on this structure. This is a CFTR in the closed state. You see that the two NBDs are far apart. They are not dimerized, hence the channel is closed. This is open state, okay? And these are the RMSF part. So you see two things here. The RMSF here, these are the NBDs over here, and these are the TMD region. So what you see here is that the TMG fluctuate to a lower extent than the NBD. And this is not surprising. The TMD is in the membrane. It is constrained by the membrane, so it cannot fluctuate too much. The NBDs are in the cytosol. They can fluctuate to a larger extent. So again, this is just sanity check. I would be surprised if this was the other way around, but we wanted just to see it. This is the same, but for this structure. And you see two things. Again, the NBDs are fluctuating to a higher degree than the TMDs, but they're fluctuating to a lesser degree than here. And again, this makes sense, because in this case, the two NBDs are dimerized, so they have less freedom. And again, this would be surprising if we saw something different. It was reassuring that we saw something which makes sense. Last thing, these are the porcupine plot, which I mentioned before, on the open structure, and you see that what the open structure is trying to do is to close itself. Not all the way around, but this is kind of the main movement. Okay, yeah, sorry. Okay, and now we're going to get into comparison with experiment. So again, collaboration with people from Atlanta. P67L is a known CF causing CFTR mutation. It could be rescued by the potentiator and the correctors, and the region and the site of this mutation is in this region over here. This is called the lasso, the lasso motif, because this part over here reminded someone of a lasso, like a rope. I don't know why. So what does this mutation do? So we ran our simulation. So this is the inward-facing conformation. This is this conformation over here, and this is the outward-facing conformation. So let's focus on here. So these are RMSF differences. So this mutation minus the wild type. So whenever you see something above the zero, this means that in this region, the mutation fluctuates more than the wild type. And if you see something below this line, it fluctuates less than type. And what you see here, especially in the inward-facing conformation, is that this region over here, NBD2, the second nucleotide binding domain, fluctuates to a higher degree in the mutant than in the wild type, which is kind of strange because the mutation is over here and NBD2 is over here. But this is what the simulation told us. Now, we know, by the way, that this mutation could be rescued by introducing this mutation. So if you take the P67L mutation, you add to it another mutation, you restabilize the protein. So these are the result of the simulation. You see that the degree of fluctuation here is lowered when we introduce the R555K mutation. All these are just hypotheses, but then the experiment was done, and indeed it was found that this mutation indeed destabilizes NBD2. So I told you that CFTR is allosteric. So we did this type of analysis, and we identify a path in P67L from the site of mutation over here to NBD2 over here. Okay? The same path also exists in the wild type, but in the wild type there is a hydrogen bond which stabilizes this NBD2. And this hydrogen bond, you see it here, is absent in the mutant. So our hypothesis is that the reason P67L destabilizes NBD1 is because it allosterically interferes with the hydrogen bond between this part of the protein and NBD2. Sorry, destabilizes NBD2 is because this mutation interferes with a hydrogen bond in this region over here. We also, by the way, looked at the distance between the two centers of masses of the two NBDs in the wild type and in the mutant. And we found that this is the wild type and this is the mutant. So the distance between the two NBDs in the mutant is much larger than in the wild type. So perhaps this is also a gating mutation. And I'm nearing the end, and I'm just going to show you one more example. It took us about 3 years to run this simulation properly. And this is called computational electrophysiology. Computational electrophysiology are simulation which maintain a different concentration of ion across the two sides of the membrane. Now, you remember from the last lecture, most MD simulations are done with periodic boundary condition. So if you take your simulation box and you replicate it many times in all directions, there is no way you're going to maintain a constant, a difference in concentration. So this requires what is known as a double layer approach or a double membrane approach. So this is our simulation cell. The problem, it doubles the number of atoms. So we are running here with millions of atoms. The CFTR, the cell, the membrane, the water, everything is doubled. But we were able to do it again. It took us 3 years. So the idea is we put one concentration of chloride on one side, a different concentration of chloride on the other side, different in concentration, and let the simulation run. So this is the pathway, the channel which the chloride take, and I hope, and yeah. Okay, and look, and this is a chloride ion. And here I would insist to run it till the end. It took us 3 years to run it, so you can spend 30 seconds looking at it. So there is a bottleneck region in this where the channel is very narrow, so it stays there for a longer time, but eventually, yeah, I know it's not that interesting, but just give it a few more seconds. And it is moving out. And we were able, and it will go all the way out. Yeah. And we were able to follow this for maybe 100 such passages, so we can get actual statistic, atomic detailed statistic on how chloride are actually moving in the channel. The really last thing is, this is the potentiator, VX770. This is a cryo-EM structure. And the cryo-EM structure found that the position of the potentiator is in this point. However, before the structure came about, people did indirect experiment and they identified a bunch of other potential sites which were to a certain level supported by experimental evidence. So just for the fun of it, we took a bunch of analogs of these compounds which were experimentally measured by Vertex, and we did this rock analysis for each and every site. And we found that actually the experimental site based on the cryo-EM is not the site that produces the best rock curve. I don't know what it means at this stage. Perhaps they use a very high concentration of the compound in the experimental setup, or perhaps our docking simulation are completely wrong. What we are trying to do now is run the same electrophysiological simulation with this compound bound to that region where we got the best rock curve, and we'll see what we are getting from there. So, a good place to stop. CFTR structure are useful. More structure are needed, but this is always true. And simulation provide insight into the dynamics of wild type and mutant CFTR. And for specific mutation, simulation offer kind of atomic level insight into the mechanism. Okay, bright future ahead, but just kind of a moment of philosophy, okay? Again, always look at your data. Whenever you are doing MD simulation, docking, any work, any computational work, always look at your data. Don't just rely on number. Again, it's probably bad practice to deduce anything from a single simulation. Repeat your simulation several times. Yeah, it's tedious. Yes, it's boring, but you have to do it. And this is probably the most important message which I'm trying to get to people. If you're an experimentalist, you will never run an experiment without having a positive control and a negative control in your setup. Computational chemists, unfortunately, don't always do that. So you run a simulation with an active compound and you get a result. Great. What does it mean? Nothing. Run the same simulation with an inactive compound and find a different result. This is when it gets interesting. But unfortunately, computational chemists don't always hold themselves to the same standard they require from experimentalists. So whenever you are designing an in silico experiment, put positive control and negative control. Otherwise, you're not doing anything. These are the people who are doing the work. I just get to travel to nice people and to nice places and meet nice people and talk about it. Thank you very much for your attention.
You stress the importance of repeats in molecular dynamics experiments. So, given that the system that you simulate gets stable over some time, what's the difference between doing, let's say, a microsecond simulation and 10 100 nanosecond simulations?
And sorry?
What's the difference between, instead of doing 10 replicates, running 10 times longer simulation? Let's say, given that your complex is stable. I admit that there are two philosophies here. So one philosophy said, run your simulation longer, another one, run shorter simulations. I don't have a strong opinion right now one way or the other. However, we did see that in many cases, interesting stuff start happening after very long time scales. Because, as I said before, MD simulations are notoriously slow to cross energy barriers. I mean, the best thing I would do, but people almost never do it, is run your simulation, start your simulation, not with different random seeds, but from different starting point. And if in this case you get the same result, you are much happier. But almost no one does it, and for good reason, because if we do it, we'll get to the conclusion that none of our simulation is probably converged, except if you have a very, very small system. Nice, thank you.
Let's say, how different should be the negative control?
So, look, if you have an active compound that, okay, so one type of simulation we sometimes do is we're doing docking, whatever, and then we take the ligand, put it in the running the simulation, and see whether it detaches from the protein, okay? So you have an active compound, experimentally active compound, you put it there, and you run the simulation, and it stays there, great. Take now an inactive compound, a completely inactive compound, run the same simulation. And pray to whoever you are used to praying that it will detach. How different it should be, it depends on the level of your simulation. The more complex your simulation is, the smaller the difference between the active and the inactive can be that may be still revealed. But as a starting point, find something which is very different. Because if it doesn't work there, it's not going to work on something which is much more similar.
Since it's a transmembrane protein, how important is to kind of do the molecular dynamics also including the protein and also the membrane to kind of, because physiologically it should be somehow, you know, like all over the protein and some parts should be lipids. So So it could change the whole electrostatics of the simulation.
If you don't include the membrane, you mean?
If you, yeah, what's better? If you include the membrane, if you don't, because you probably didn't include it.
No. All the simulation, hold on. All the simulation on full-length CFTR included membrane. Otherwise, I'm sorry if this was unclear. See, that's the membrane. All the simulation, whenever we are running MD simulation on full-length CFTR, we are always include the membrane. If we're running just on NBD1, we are making the approximation that fine, we can discard the membrane. But there is an interesting question to which I still don't have a good answer. Which membrane composition you should use? We try to run, we know the composition of membrane of CF patient, and we try to run the simulation with this, and the conclusions and the results were inconclusive in terms of whether it affects anything or not. But the composition of the simulation of the membrane might be very important. Look, in general, whenever you're trying to reproduce an experiment, you should try to make your simulation as much as possible similar to the experimental setup. It's not always possible.
Did the cryo-EM structures from the PDB data bank, I guess?
Yeah.
Did they come also with the membrane? Or
No.
have to actually...
You have to add the membrane. There are algorithms which tells you how to insert your protein in the membrane, and there is a whole procedure involved. But no, the cryo-EM structure comes without the membrane. The crystal structure typically comes without the membrane. You need to do it yourself.